on the technical journey ahead. It is my privilege to welcome you to the plenary session of MEICON 1.0. This session brings together four distinguished speakers who are thought leaders in their respective domains to enlighten us with their insights and expertise. We are delighted to have two speakers with us here in person and two joining us virtually. Their talks promise to enrich our understanding of emerging trends and innovations shaping the future of mechanical and allied engineering disciplines. So let's proceed into the technical brilliance of this session. The first speaker of the session is Dr. Akshay Runchal, a distinguished industry mentor for our department. We welcome you, sir.
Thank you very much,
Doc-
and
uh,
for a nice introduction. And I'm glad to be able to join you on this occasion and this celebration, this exhibition. And I wish you the very best.
So I would like to give a very brief introduction of yours, and then I will be inviting you to deliver the session, sir.
Sure, thank you.
Okay. So Dr. Runchal is the president and founding partner of ACRI, Los Angeles, California. Sir is a distinguished figure in the field of computational fluid dynamics, boasting over 50 years of experience in simulating flow, heat, and mass transport processes. He earned his PhD from Imperial College London in 1969, where he was instrumental in developing the finite volume method under Professor Spalding. Dr. Runchal began his academic career at the renowned Indian Institute of Technology, IIT Kanpur, and has since taught at various prestigious institutions, including Imperial College London and the University of California. In 1979, he founded the Analytic and Computational Research Incorporation, that is ACRI, in California. He has also established the CFD Virtual Reality Institute in Dharamshala, India, promoting CFD education and research. Dr. Runchal's contribution have significantly advanced CFD. We are overjoyed to have Dr. Runchal as our guest in this conference. So now I request Dr. Runchal to deliver his talk. Sir, please.
Thank you very much, sir. And it's my pleasure to join. And CFD is very close to my heart. I have done it for 50 years, and I couldn't be more happy than doing it. So I think let me just figure something out here. Let me see how I can project my screen. Can I? Let's see, I'll screen share. Share. Can you see my screen?
Sir.
Are you able to see my screen?
Yes, sir. We are able to see your screen, sir.
Okay. All right. So what is happening in CFD is something very interesting right now. We are at a very interesting juncture in history. Just as 1960s was a very, very important period, I believe the 2020s will be so. So I'm going to talk today about CFD and machine learning. In this talk, I was helped by Dr. Rao and Dr. Rajagopal Pachala of CFD Virtual Reality, and I'm very glad that OBJ University invited us to talk about it. Is my voice coming out clear? Just want to make sure.
Yes, sir. You are perfectly audible.
Okay. So here is the summary of my talk, why we do it, what is machine learning, how to proceed, and I'll talk of a case study, and then I will shift my attention to what I think is happening to CFD in the future. So CFD today is a combination of science, and the science comes from Navier-Stokes equations, Boltzmann, thermodynamics, things of that nature, which is physics with well-defined mathematical basis. But that is not all. Then we have to write a computer program, then we have to solve those equations, we have to make some assumptions. So I call that all art. It's in designing an efficient system with the limited computational resources that are available to us. And finally, there is what I call the guesswork, which is the largest part of CFD today. It so happens that many aspects of real fluids and their behavior are very poorly understood. The best example, of course, is turbulence. We are still trying to understand turbulence after 200 years. So machine learning can help both with the art and the guesswork for sure, but also it can help verify the science when there is empirical data. Don't forget that Newton's laws stood for a long time before Einstein came, and we had to modify our science. Something same can happen to Navier-Stokes equation, to Boltzmann, and to thermodynamics. So what are the challenges today in CFD? Many challenges. Biggest challenge, of course, is that you must have faced it too. You never have the computational time and storage that you really need to adequately solve a problem. You always say, well, let me increase the time step or decrease the number of steps or increase the size of a grid or whatever it is so I can do the problem in the time I have. I've heard of cases where simulations have lasted for months. Then there is, of course, once we get these millions, billions of algebraic equation, we can't solve them adequately. Matrix solvers, there's no direct solver, which is possible today, which is efficient today for large matrices that we generate, billions, millions of points. These algorithmic issues, after 50 years, we still don't understand what is the best way and what is the most general way to deal with mixed flows, convection, diffusion, there is electrophoresis, things of that nature come up, which we don't need how to deal with. Then there are two kinds of uncertainties. And first one is, of course, the lack of knowledge. We call it epistemic uncertainty. What this means is turbulence is the best example. We don't still understand. There are many turbulence models. Anytime there are many models of something, that means we don't understand it, right? There is one Navier-Stokes equation that defines the flows, but there must be about 50 turbulence models, if not 100. So everybody has their opinion. Same thing happens with reaction kinetics, multiphysics, things of this one. And then there is a second uncertainty, which we cannot easily eliminate, which we call aleatoric. And that means that there is inherent randomness in the process itself. For example, if you take atmospheric flow, who knows the initial and boundary conditions at a given time? There's a probability the wind could be within this range and approximately from this direction, but nobody knows exactly at 2:35, 30 seconds what the wind would be. There's no way to measure it. So machine learning can help with all these aspects. So what is machine learning? Firstly, a very simple definition. It gives the computers the ability to learn without explicitly program. That means we don't have to program the computer. We have some algorithm that the computers have inside them, and it trains itself to do that, right? There's a more complicated definition that Tom Mitchell gave in 97, which says, and this is the precise definition, a computer program is set to learn from experience, E, for a specific task and a given objective and some performance measure, right? And if that performance measure increases, improves with computers, we call it machine learning. That we call it machine has learned, right? Now, the practical definition that we have come up with is that machine learning is really nothing more than fitting models to data within a certain range of believability, minimizing the error. So machine learning is nothing new to us. It has been around for a long time now. For example, anybody who used a telephone today, a smartphone, uses machine learning. Natural language acquisition, you translate speeches, you go from one country to another, and the machine tells you what to say. That's all machine learning. Medical imaging is full of machine learning, video processing, all these are examples. So how do we do machine learning? This is something called an artificial neural network, ANN, or simply a neural network, which is at the heart of machine learning. Now, sometimes we call a machine learning a deep neural network, DNN, rather than ANN. All it means, I'll give you an example, all it means is that we have multiple layers between the input and the output. So machine learning can perform very complex tasks, but it does require training and validation data. So that is very important. And typically we have to have some models or hypotheses that we create or generate from the data, and then we fit those model parameters by minimizing a objective function, a loss function, or a gain function. So there are two kinds of machine learnings. One is supervised, one is unsupervised. Supervised is when we know the answer to the problem. If we know the answer to the problem, we turn a machine and say how to come out with the correct answer, right? Okay, that is supervised learning. So we minimize the loss function, the error, by training the machine to say, okay, this is the data I have. Make sure whatever you predict matches that. Okay. Now, unsupervised learning is what usually is the case with fluid dynamics, with CFD, where we do not know the correct answer. We seldom know the correct answer for CFD problems, except for very simple ones. Laminar flow in simple situation, yes, we know the answer. Most we don't. So machine learning has to find patterns. It has to do order reduction, clustering, compressing data to come to one. So what do we get from machine learning? We get two kinds of outputs. One could be continuous variables. For example, we could predict the velocity and temperature in a whole field at 500 points, 5,000, 5 million points, and that would be called regression, and the machine learning would learn to do that. The other one is a very simple classification where the output is a discrete value. It could be a binary value like, is this photo a cat or not a cat? That's a very simple example, right? Is this flow laminar or turbulent? But then we could also have multiple outputs. For example, a multi-phase is a very good example where is it a bubbly flow? Is it a slug flow? Is it a churn flow? Is it an annular flow? So that is a classification. So there are two kinds of outputs we get from that. Now, here is a typical machine learning system where there is an input layer here, there is an output layer, and in between we have a bunch of electronics which has some functions built into it, and there are multiple units of that function, and they are taking the input and doing something with it and coming out. So basically this part is basically data fitting. This is basically some kind of a form fitting for certain equation, could be exponential, sinusoidal, whatever you want to use, which best fits the system. So the first example of machine learning as an approximator was as a function approximator by Hornick and his team, and that happened in 1990. The first time somebody solved a partial or an ordinary differential equation was RAigarh and his students in about 10 years later. So this is a path-breaking paper and was the first example of a partial differential equation being solved. Now, let's look at what is physics-informed machine learning. Now, what physics-informed machine learning basically is that we take a system that we had before, like ANN or DNN, multiple layers in between, and we embed Navier-Stokes equations in it. How do we do that? Here is the input. That means, it could be any boundary conditions, input condition, whatever you want to give as the input to your equations. You put that to a neural network, which has a function built into it. A neural network predicts something. You take that something and put it in the Navier-Stokes equation, and you solve the Navier-Stokes equation. Are the Navier-Stokes equations satisfied? Yes. Yes, we have a trained, physically informed neural network. We don't solve the Navier-Stokes equation. We go back, we say, hey, your function is not right. Retune it. Give me another output. So you go back and forth. So once trained, prediction is very non-iterative. Once the system is trained, basically the next simulation you want to do could be minutes, because basically you have a tabulation of values, and that tabulation says what is the output for a given input. And that's all that happened. You have to look up a table, or it could be a function. Analytical function could have been defined. They say, oh, here is a function that fits it, and this is what it is, okay? The second advantage is that we can get the sensitivity of the input to the objective function very easily. And we can get solution gradients which say, if you change X input by 10%, how much does the output change? Which is very useful in real life situation. So what combining PIN with CFD does is it better gives confidence in the results. It's less of a black box. And when sometimes you can also helps you know situations for which it is not trained. You have some validity. Let's say you trained a system from 1, 2, 3, 4, 5, 10, and now you ran a situation where the input is 11 rather than 1, rather than 1 to 10. Well, if you predict it, you have at least some confidence. It's of course not absolutely sure, but it's some confidence its system is not behaving strongly non-linearly or there's no disconnectivity, then the 11th would give you some answer for it. So it's very useful in real life. So results can be better understood. And the advantage for CFD is that we can also make it work with no data. In other words, there are many situations where you know the Navier-Stokes equation describes it. We have a certain input, we have a certain output, and because we already solved the Navier-Stokes equation, we can say, hey, that's fine. We don't need any training or validation data. At least Navier-Stokes equations are satisfied. So machine learning at CFD gives us convergence acceleration. We can, for example, tune relaxation parameters, tune how many iterations to do. We can also do meshless computing because it doesn't require a mesh, right? We can take one point, discrete point, 10 discrete points, and train a machine learning to say, hey, Navier-Stokes equation satisfied that 10 points, right? Okay, it's meshless computing. Many times when you do the CAD models from the geometry, there are holes in it. There are discontinuities in it. So we can pick those up with machine learning because we'll know what happened, right? But one of the best uses is also for inverse problems where we need the sensitivity of an output to an input, or we want to find out this happened, what was the cause? Inverse problem, right? So all that can be done. So it basically is a fairly powerful tool. We can also use machine learning for augmenting the physics. For example, I can say there are certain situations where K-epsilon model doesn't apply. One of those situations is when you have a lot of swirl or the streamlines are very highly curved. The typical standard K-epsilon model will not work for those situations. Well, I can add a term for that, and I can say, I have some data for this situation with strong swirl. What should be that function that makes it match the data, right? So we are now modifying our model for a specific situation to solve it. That is another use. So turbulence modeling can benefit a lot. I won't go into the details. You can look at it, and anybody who's interested, I will make these slides available to you, and you can write to me. Similarly, for multi-phase flow, which is a highly nonlinear flow, nobody fully understands it yet, we can use machine learning to augment our physics. Some notable applications in the past there have been many. There have been turbulent combustion has been done, multi-phase flow, structure dynamics, many applications have been done with PIN. Some of the more different and noticeable, there was cardiovascular application to cardiovascular flows, where patient-specific blood geometry was used to figure out what is the wall shear stress, which is where the artery may rupture, and that part. Similarly, aneurysm, which is basically a bubble in a artery, or which can risk rupture again. So that is typically happens. It couldn't happen in the rest of the body, but it's very important if it happens. Very disastrous if it happens in the brain. So that has been done, and there's been a lot of uncertainty quantification to learn whether a probability distribution Gaussian rather than let's say non-Gaussian, like a beta function, something like that. Okay, and we can predict mean and variance. So there have been many uses already. Now, one thing we do with machine learning, other than predicting a system, is also to essentially make a digital twin of it, or a essential, what I call is surrogate models. What we do here is that many situations come where, for example, where you only have an objective function and you don't need to worry about the details. I'll give you one example. Let's take the flow in an aircraft combustion engine. Now there's a combustor, there's a compressor, there's a combustor, then there's a turbine at the end which generates the energy. So what comes out of the compressor A lot of things happen in the compressor, very complex. Sorry, not compressor. The hot part, the engine, the actual combustor. A lot of things happen in the combustor, right? Typically, people use millions of points to define that combustor, right? But what is important to the turbine is not those millions of points. It is what comes out of the combustor goes into the turbine. And only thing that matters is what is the temperature and what is the variation of the temperature, because that determines how much stress is placed on the turbine blades, right? So objective function is just what we call a pattern factor. Pattern factor is the variation of temperature, right, with radial or axial direction. That's all that matters, right? So what we can do is we can make a whole model, a digital model of the combustor. And then we don't have to simulate the combustor. We just get the objective function directly, right? So that is, it's similar to the old style lab physical model where you had a boat, you want to say how it performs in a river or in an ocean. So what you do is you take a water tunnel, you put the boat in there, you make a model of it, which has the same fluid number and same everything else. And you say, okay, now this represents what happens really. So all we are doing is instead of the lab physical, we have a computer at the core of it, which is making the physical model or something similar to physical model called a surrogate model, right? So it can be used when CFD is very expensive, like in the aircraft combustor situation. And also the other advantage of it is that once you do it, it doesn't matter it's a 1D, 2D, 3D system. Whereas if you do a CFD computation, 1D is very simple, 2D is 10 times more expensive, and 3D is 100 times, and maybe 3D with time dimension transient would be 1,000 or 5,000 or 10,000 times more expensive. So here is how a digital twin works. You have a physical asset, right? And you want to create a machine learned model called a digital twin. So all you do is you take that physical asset, you simulate it. Oops, I need to go back. Okay, so you train that model to, with all Internet of Things, you can get the data, you can get data from the cloud, you can get data from the databases, or you can get data from Navier-Stokes equation. You take all that data, you put it in a physics-informed neural network where Navier-Stokes equation is again here, and you put that in the you put that in that, and what you do is you get a machine learned model called a digital twin. Now, next time you need to do it, you just say, okay, this thing changed, this is the output for that. So it gives you a comprehensive model of a very complex system, and is essentially a digital twin of the real situation. So here is to make it clear, here is a study of that I will show you. This is a typical automotive cooling system. It has a radiator, it has a pump, and it has a heat exchanger at the back there that you perhaps don't see. I guess my picture is there. I don't know how to move it. I'm not going to bother to move it there, but there's a heat exchanger there, right? So what happens is that this pump is a two-phase flow and it's rotating, right? Now that is a very expensive thing to put in a rotating frame and simulate this pump. And this pump is a two-phase flow. There is air trapped in this. There are air bubbles, right? So it's very expensive to do combined calculation. The whole system is on the order of meters. And look at these tubes. They are on the order of millimeters, right? So your time, if you do a CFD simulation, your time is going to be determined by these tubes, or it's going to be determined by the rotation speed of this pump, right? Okay, you'll have millions, billions of points to do that. Now, what we can do is we can replace this with a digital twin. And we, as I said, this is the complexity. And so what we do is we take this part of it. We say, okay, we're going to make the digital twin for the channels, for example, or we're going to make a digital twin for the pump, right? And that means the next time you simulate the system, you just plug in, you look up a table for what is happening here. You look up a table for what's happening here. Here is the input. This is the right output for that, right? Or here's the input. This is the right output, right? So you replace these complex components, which are very expensive to compute, with just a table lookup, okay? So those are digital twins, okay? So here is the case of a pump. where this is the typical flow. You can see how it's breaking up. It's got air in it. It's got solids in it. And if we do 1,000 of these simulations by standalone once for all kind of various conditions, then we were generated what is the output. Only thing that matters is what is the input and what is the output. That's all. What is happening inside the pump doesn't really affect us as far as the cooling system is concerned. What is the objective cooling system? Not to understand the pump. We don't care. Okay. What we care about is that is it effectively cooling the engine, right? So for that, we replace this with a table lookup. So here is a case where we do a simulation of the one pipe. In this case, we did 3 pipes. I'll show you. But anyway, you take a pipe, the small pipe, one tube. There are hundreds of these tubes. You take one tube and you do a complete simulation from time, t to whatever time is of interest for a long time till you get a semi-steady, or if not steady, then a periodic situation. And you do all that simulation independently. Now, this is very simple to do. You're just doing one tube, right? You're not doing thousands of tubes and being affected by that, and you can do it offline, right? Now, then you use that to actually simulate the system. And here is what we did with 3 tubes. We just took 3 tubes and simulated that. One is a tube that represents the end, and one is a tube that represents the other end, and then the tube somewhere in the middle, because some tubes are, location is such, right? So this tells us what it is. And here is the difference between the predictions from the machine learned model and the predictions from the CFD simulation from Navier-Stokes equations. And so in this case, this may not be visible to you, but this is about 1%, and this is about 2% here. So within about 2% of accuracy, we can say that our system can give you a value within 2%, which is quite often very acceptable. So here is a summary. You perform CFD simulations for the component's interest. You call a neural network for the CFD solver. You combine with empirical data, and you have a digital twin. So then when you come to the complex system, you remove the mesh that is representing the system, that part, that component with the one, and you have a digital twin that is given you an accuracy and a speed up. Accuracy, of course, now is within certain percentage based on the training that you've done. So the future of CFD is that more demands will be placed on the CFD to simulate design of design conditions. And what is very important is that increasingly the design engineers want to say, hey, I have this CFD, I have this heart, it's pumping, but also this heart is, vibrating. It's the system in which is controlled is not fixed. It's moving with time. I want to do the structures also. I want to see what the pressure, why does it expand and all that. So I want to put the structure with it. Maybe I want to put electromagnetics, vibration, acoustics, all kind of things are happening more and more. Now, we don't have the compute power to deal with all that. So the future would be high simulations with PIN or DNN. Okay. So the code will need to be more robust. Today's codes do not give us reliability. Okay. You take the best code. I don't care what that is. I don't care if it's a code that is used widely or if it's a code that is used only once. You go and ask the code developer. You ask the next time the company that is giving you the code, hey, what is the liability? Can I sue you? Can I charge you $1,000 per infraction if it doesn't meet your accuracy of your predictions? Nobody would tell you, nobody will give you a guarantee that your code is giving you a result that they will vouch for, right? That is not how practical situation should be. If you go buy a TV, for example, and it breaks down in 2 days, you can go back and ask for your money back, right? Try doing that. If you get wrong predictions from a code, try going back to the company saying, hey, give me your money back. It didn't predict correctly, right? So future of CFD codes can be learned from what happened to the car. In the initial stages, when I was a young man, it was the engine of the car that you cared about. Okay, we cared about the engine. How many cylinders? How many something else? Okay. And sorry, in a meeting, call you back. So what we want to do, sorry about that. I'm sorry, I'll have to call you back. I'm in a meeting. I'm I'm sorry about that. So to buy a car, you don't look at the engine now. You look at what kind of car you want. You want a car that commutes from place A to place B, or you need a car, you're a race driver, you need a car that goes on the track and beats everybody else, right? And then you look at, is it comfortable inside? What's the gas mileage? If it's an electric car, how far does it go? You look at, is it comfortable inside? It is warm inside? Does it have GPS? And all those things. So you're looking at the interface, and your objective is to drive the car. Do you really care about the engine? No, you don't. The young people, how many young people who have bought a car ask about what is the engine? In my days, when we bought a car, I knew it is a 4-cylinder car or a 6-cylinder car. It's a V setup. What kind of carburetor it has? What is the displacement? Those are things we care about. Nobody does that. So same thing is going to happen to the CFD. Nobody is going to care about the engine. Nobody is going to care about CFD. You want to care what CFD can do as an engineer. How can I use this CFD to do what it is? It's too cumbersome to use today, long training period and poor reliability. And therefore, what is going to happen to CFD is that we would have improvements. Of course, there'll be better science as we do more and more research. Of course, we'll have better computer resources. But what is going to change it is the machine learning. We are going to develop digital twins for things like disaster response or important components where we can quickly do it. We're going to do that with physics-informed neural networks. We're going to do that with engineering virtual reality, where we can give a command to a CFD code with a built-in voice or interactive command. So what we'll have in the future is an app, no different than the other apps that you have. And you will tell the app, I have an aircraft engine, and here is the combustor, and this is the fuel I want to do. Give me a design that meets this pattern factor limitations. Okay, so you will interact with that just like you interact with other apps, and you will, in a natural manner, hopefully get your design objective. So that is where you would not care about the engine, which is the CFD, that will be hidden from you. So future of CFD modeling is CFD engines that are invisible to the design engineer. I'm a mechanical engineer. I want to design an aircraft combustor. What do I care how I get the answer? I want it to fly a certain plane with a certain thrust and all those things, right? I do it by CFD, I do it with a magic, I do it by the intuition. How does it matter? People did it for intuition for a long time. They didn't have CFD, right? Okay, so we will have special purpose apps and tools, and this will be achieved by virtual reality, AI, physics-informed networks. Thank you very much. I hope I encourage you to do and learn CFD and practice it, and I hope that will be that's it from my side. Thank you. I've enjoyed it, and I hope you do. Thank you very much, sir.
Thank you, sir. That was truly an enlightening experience for all of us. As a student of thermal engineering, I must say we have much to explore and understand to fully grasp the depth of your presentation. Thank you so much, sir.
Thank you.
So we now proceed to the second plenary speaker of our session. Decarbonization is the key to achieving sustainable advancements through innovation. And today we have with us an eminent technical expert from the industry who has been working diligently to achieve the holy grail of decarbonization in the steel industry. I now welcome Sri Vishwabandhu sir, Vice President, Low Emission Steel, Jindal Steel and Power, RAigarh, Chhattisgarh, India. Sri Vishwabandhu sir holds an MTech in Metallurgical Engineering from IIT Kanpur and is a certified energy auditor by the Bureau of Energy Efficiency, BEE, Ministry of Power. With over 38 years of experience in iron and steel sector, his expertise spans energy audits, carbon emission calculations, process improvements, and consultancy in the steel sector. He is also involved in projects with UNDP and GIZ on energy efficiency and green steel initiatives. Under his leadership, JSP has implemented innovative technologies to enhance energy efficiency and minimize environmental impacts. Bandhu's commitment to sustainable industrial practices contributes significantly to the advancement of green steel production in India. I invite Sri Vishwabandhu sir to address the gathering. Sir, please.
Yeah, presentation is loaded there, no?
That slide change.
Slide change.
सर कुछ चेंज करना है slide.
हाँ,
रेंज का इशू है यहाँ से.
रेंज नहीं, एक मिनट, ये नहीं हो रहा ना. हाँ. So thank you organizers for inviting me for a talk in the plenary session. So my topic is recent developments in green steel production. And this green steel. Now, what this really means, green steel? In fact, in the world, still there is no definition for the green steel. But India has taken the lead and has devised a definition for the green steel. I'll tell you. See, now the focus of this conference is on sustainability, innovations or research, developments, whatever, automation and all that. But now the all roads leads to the sustainability part. And there are various dimensions of sustainability, and decarbonization is the one of the very important, very prominent levers in the sustainability. And this steel industry contributes a heavy amount of CO2 emission the world over as well as in India. As far as the world over is concerned, the global scenario is concerned, the CO2 emission is something around 8%. The steel industry contributes about 8% of the CO2 emission globally. And in India, it is about 12% of the total CO2 emission. So that indicates the importance attached to the steel sector and the decarbonization in the steel sector. So my focus will be on the steel because that I'm a core technologist with the iron and steel making sector. So as far as the steel is concerned, I'll give you a brief about how the steel is produced. Unfortunately, the steel cannot be produced from the raw material, that is the iron ore, in a single step. So we are producing the steel in two steps. The first step is conversion of iron ore into iron, and then in the second step, we convert iron into steel. So up to the steel making stage, here up to steel making stage. See, this is the raw materials. These are the iron making routes, different iron making routes. This is the steel making route, and this is the refining of the steel. And then the steel is casted in different shapes on the continuous casting machine. Up to this stage, we call it as a crude steel. But none of the steel is used at this stage. It has to be finished. So the most of the finishing is done in the rolling, by the rolling. So whether we produce bars, rods, wire rods, angles, channels, beams, columns, rails, or even plates, sheets, everything is by the rolling. So then we call it as a finished steel. Right? As far as the steel production is concerned, the global steel production is something around 1900 million tons. It is much more than all the materials combined together throughout the world. And undoubtedly, China is the leader in steel production with a contribution of more than 1 billion tons. Exact quantity is 1019 million tons. Although India is placed ranked number 2 in the list, but we are much behind than the China. We are producing something around 140.8 million tons, while China is 1019. So we are not even 8% of that. Or let us say we are about 12% of that, China's. But only 6% of the world steel production. Somewhere you may find this figure as 144 million tons. That is also true because this 140.8 million tons is based on the calendar year. But 144 million tons is based on financial year because we normally record our steel production on a financial year basis. Now, this is the growth path of the steel sector in India. And if we see from 2002 to 2023, we have achieved a compounded annual growth rate of almost 7.4%, which no country in the world has achieved this rate. So we are, although we are number 2, but we are the fastest growing as on date, as far as the steel production is concerned. And some of the facts about the steel industry in India. We have a capacity of 179.5 million tons in India. And Ministry of Steel is planning for a capacity of 300 million tons by year 2030-31. That is as per the National Steel Policy designed in or formulated in 2017. And production is 255 million tons. What we are planning in this decade, that means by 2030-31. But as on date, we are at this 23-24, this 22-23, 23-24, and finished steel is we are planning 240 million tons by the end of this decade. So this is the crude steel, this is the finished steel. So we normally end up a yield of around 92%, something like that. So 144 million ton crude steel, so 136 million ton finished steel. Okay. And as of now, we are a net importer of steel now. Although for the last 5 years, we were net exporter. And our exports were more as compared to the imports. But last financial year, our exports were little less, almost 7.5 million tons. But our imports were 8.3 million tons. And this year also, this financial year also, as on date, we are net importer of steel because some of the cheap steel is coming from China. We call it a dumping also. This is the world scenario. Now, coming after this steel statistics, we are now coming to the CO2 business because this is one of the important levers in sustainability. See, in the world, the steel production was 1892 million tons in 2023, and the average emission intensity of CO2, carbon emission, what we call it as, and we also call it as a carbon footprint. That was 1.91 tons of CO2 per ton of crude steel. That is the world average. But in our average emission intensity is 2.54 tons of CO2 per ton of crude steel. Does that mean that we are very inefficient? Our industry is very much inefficient because the average world is emitting 1.91 million tons, but India is emitting 2.54 million tons. On the face of it appears that Indian industry is not up to the mark as far as CO2 emission is concerned. but that is not correct, because let us see the levers where we stand as compared to the world. See, these are the levers. The world is using around 31% of scrap in the steel making, but we are using only 21% of the scrap. And scrap intensity as far as CO2 emission is concerned is zero, because we need not prepare the raw materials for that. We don't need pelletization, we don't need sintering, we don't need any iron making stage, we don't need any steel making stage. Just melt it. You require only the electricity, that's all, nothing else. So that is a very big contributor in CO2 emission. Larger the quantity of the scrap I use in my steel making mix, raw material mix, the lower will be the CO2 emission, and vice versa. Then in the world, natural gas availability is very high. You see, a lot of the cities in the world, they are sitting on the seashore, and Arab countries, they are on the seashore. So, lot of natural gas is available. So, the CO2 emission intensity in natural gas as compared to the coal, which we are using in most of our operations, it is certainly CO2 emission intensity in case of natural gas is much less as compared to the coal and the oil. So emission intensity of power is low in the world as compared to our India. It is again the same thing, because most of the world power plants, they are based on gas. Rather, our power plants are based on coal. Then quality of the raw materials, more particularly the ore, the quality is high and our quality is comparatively lower. See, the word best iron ore comes from Australia and Brazil, which has a very high iron content and very low impurity level. While in our case, it is not that. And hence, combining all these factors together, our emission intensity is considerably higher as compared to the world average. So let us see the among the world also. Let us see the some countries how they are performing, how their CO2 emission is recorded. Uh, India 2.54, China it is 2.01, Ukraine is 1.68, Russia is 1.65, Japan 1.61, and you see the USA 0.79, very less. Turkey 1, Europe 1, almost 1. Why? Ours is 2.54. Why USA, Turkey, and Europe, they are so low in CO2 emission? It is again because of the mainly because of the two factors. That is, one is the scrap percentage. USA uses about 75% scrap in their raw material mix. Turkey also about 70% scrap. Europe also about 65% scrap. Number one. Number two, renewable energy content in their power mix is much higher as compared to India's. India has lately has increased its renewable energy component in the overall power mix to a very good extent. Now we are about 45% of our power mix as far as the capacity is concerned is renewable energy, combining solar, then wind, then hydro and nuclear, all combined together. And what is the plan for India as far as the CO2 emission is concerned, and hence the sustainability part? See, currently we are at this level, 2023-24, 2.54 tons of CO2. And Ministry of Steel has given the target of controlling the CO2 emission to 2.2 tons of CO2 by 2029-30. And we have to align with that. That means this boils down to something around 15% of the reduction in CO2 emission in next 6 years. Now, why there is so much fuss about the CO2 emission? What are the implications of this CO2 emission on my sustainability part. See, because of the CO2 emission, our CO2 percentage or CO2 ppm in the atmosphere is continuously rising. Now, when if we see the before industrial period, industrial revolution started, let us say 1800, the CO2 CO2 in the atmosphere was something around below 280 or say around 280 ppm. But today we are 1.5 times higher than that. We are more than 420 ppm. Some may think, how does it matters? It is in ppm. Whether it is 280 ppm or 420 ppm, how does it matters? But this matters a lot because we are disturbing our environment, and environment plays its role in many ways. One of the thing is that global surface temperature rise. And you must have read or you must be aware about the global warming. And CO2 is the major contributor in this global warming because of the quantity of CO2 which is going into the atmosphere, which is not absorbed uh, by uh, yeah, by the amount which you are emitting. So there is a net increase in the CO2 emission. Net increase in the global warming. And today, if we see a baseline up to a 1900 year, then we are about 1.3 degrees higher global temperature. And the direct effect of this, there are many effects of this global warming, but one of the direct effect is the sea level rise. And if we see the 1880, if we see the base year, then the sea level rise has gone up to almost 250 mm rise in the sea levels. You can imagine, you can gauge what are the implications of the sea level rise. It can be very much catastrophic in the years to come. And what is more glaring is the rate of the CO2 rise in now coming years. In the last 10 years, if you see, 4.62 mm per year. While in the this 20 years back, it was only 2.27 mm per year. So what should be our strategy to control this CO2? So our strategy should be in with all this. These are the levers, various levers, and the Ministry of Steel is actively supporting the industry on all these fronts. So we have the base year now 2024 and short term 2030, medium term 2047, long term 2070. And now everybody knows that India government has committed to the UN that yes, we will be carbon neutral by 2070. Although this is applicable to developing countries, including India, but some of the developed countries, they are given the target up to 2050. That means carbon neutral. Carbon neutral means no net CO2 emission into the atmosphere straightway. And these are some of the factors how we can achieve this carbon neutrality by 2070. I'll just go through it. Energy efficiency, the very first thing, because this doesn't involve any capital investment, any capex. Then renewable energy, again, maximize the use of pellet, increase use of scrap, green hydrogen, biochar, CCUS. And then these are the ultimate technologies, molten iron, molten oxide, electrolysis, and all that. And this is the roadmap developed by the Ministry of Steel, how we can achieve zero carbon emission, net zero carbon emission by 2070. So here are the targets given to various countries to achieve net zero emission. So if you see some of the developed countries, they are given the target up to 2050 only, like US, EU, European Union. They are given the target up to 2050. China has taken the target up to 2060. Japan has taken the target up to 2050. India, 2070. While Canada, Mexico, South Korea, and all that, Brazil, by 2050. And that will be the ultimate technology which will be coming through. And some of the plants have already started doing work on that. And that is the CO2 utilization. Because whatever the fuel, if I use in my process, in the steel making, iron making, steel making, or rolling, the carbon emission will be there in the form of CO2. Now, if there is CO2 emission into the atmosphere, how can I control? How can I be carbon neutral in that case? In that case, I have to capture the CO2, convert it into some useful chemical like methanol, ethanol, or something like that, or use it CO2 for calcium carbonate, or use it into the aerated drinks or something like that. Or even if cannot be converted into some, although technologies have been developed to convert it into ethanol, methanol, ethanol, but still I can have the option to store it somewhere under the seabed and all that. And different projects are already installed for storage as well as for utilization of CO2. So these are the various countries, what they are doing for CCUS projects. And India has also started this journey on the CCUS. And these are the some of the developments, R&D, which is going on in India. IIT Bombay is actively working on that. Even CSIR, IMMT, Bhubaneswar is also active in that. And JSP, Jindal Steel and Power, we have also taken initiatives for this CO2 capture and utilization of CO2 into some gainful chemicals. And we have tied up with IIT Bombay to convert it into CO or some other chemical like methanol. So JSP is also going with this short-term strategy, medium-term and long-term. In short term, we are already working on energy efficiency. We have identified various schemes where energy can be reduced. Then material efficiency, yani that means we are working on waste management. And whatever the waste which is generated in the process, whether it can be recycled or whether it can be minimized, we have identified the various scopes in that. Operation efficiency, for example, yield improvement and all that within the existing system. Then in the medium term, we are going for renewable energy. I don't know, some of you might be aware that JSP is under its arm, JSP Renewable is putting up a 2800 megawatt of renewable energy, which is a combination of solar as well as wind. So solar is coming up in Rajasthan and wind is coming up in Tamil Nadu. Okay, so we'll get the energy from that, and straight away we can reduce our CO2 emission. Then CCUS, as I told you, we are capturing CO2, and then IIT Bombay is converting that CO2 into some useful chemical. We are also discussion with some parties for using biochar in our process, various processes. And in the long term, we are going to green hydrogen and process transition like gas-based DRI. Okay. So with this, here in JSPL Angul, we have already captured CO2, and then IIT Bombay is converting that CO2 into chemical. So this taxonomy for green steel, the Gazette notification has come just recently, 3 days back. And in fact, I was under Ministry of Steel before joining Jindal Steel RAigarh, and I was a member of this taxonomy for the green steel. And we that time we have defined what is the green, what the green steel definition will be. In the world over, no country has defined green steel, but we in India have defined the green steel. And green steel will be called when the CO2 emission is below 2.2 tons of CO2 per ton of steel. So, and they have Ministry of Steel has devised a star rating for that, just like electrical equipments. 5-star, 3-star, 2-star, and here also 3-star rating if the CO2 emission is between 2 to 2.2, 4-star rating if the CO2 emission is 1.6 to 2, 5-star rating if the CO2 emission is less than 1.6. And the green steel certificates will be issued. And government is now, Ministry of Steel, maybe in the next budget, it has all the probability that Ministry of Steel will incentivize the plants which will be producing green steel, and they will also push the green steel making by preferential purchase of green steel in its government projects. So that is how the government is supporting, and this is the government initiatives, development of green public procurement policy framework, and Ministry of Steel to propose framework to Ministry of Finance, that is already ready. And for public sector projects, it will be using the green steel only. And for private sector, it will enhance the ESG rating points for green steel consumers. So your ESG rating, if it is high, so there are multiple benefits of ESG rating. If it is good, then international investors, global investors, they will put the money at a lower capital cost to your plant or to any industry. So that is all about this CO2 emission and the green steel. Thank you very much. Any questions?
Any questions from the audience?
Yeah, any questions? Yeah.
Mike, sir, is there any industry in India which is producing a 4-star green steel?
See this notification has recently come just 3-4 days back. But there are many industries in India which are already producing green steel. Why? I am telling you. What are those industries? Those industries are which are making steel by using scrap. So there are various geographical locations in India where they are using scrap only for making the green steel. For yes, this Punjab area, there are about 20-30 units which are producing green steel. Then Bhavnagar area, Gujarat area, they are also producing green steel because they are depending only on the scrap. So if we are using scrap, say 100% scrap, so only power consumption is there. So their CO2 emission is only 0.6, 0.7 tons of CO2. Kalyani Steel is one of the very important industry in India, and which are highly exporting alloy steel to the world. That comes under green steel, maybe 5-star.
Efforts of Jindal for using biochar and pellets for bricks in production of steel.
See, Tata Steel has already used the biochar in its blast furnace. And we are also contacting parties for use of biochar in our blast furnace. Because when I use in the blast furnace, my expensive coke is reduced, and PCI is reduced. PCI means pulverized coal injection, which is imported also with a high carbon content. So at least I know these two plants. Tata Steel has already experimented on it, and we are within maybe next year, we'll be starting with the using of biochar in blast furnace. Not for the power plant for the time being, but for the blast furnace, because we'll be replacing high cost coke in that. Yeah. Yeah.
सर यहाँ माइक का जरूरत नहीं है 110 छात्र रहते हैं क्लास में माइक का जरूरत नहीं है हाँ सर कार्बन डाइऑक्साइड जो है इट इज अ वेरी गुड फूड फॉर द प्लांट्स ओके यस और खूब सारा कार्बन डाइऑक्साइड भरा है मतलब पौधों के लिए खूब सारा खाना है तो मैं दुखी हूँ कि सुखी हूँ यस see when anything which is good suppose almonds
cashew is good for my health.
नहीं खा सकते।
Okay, but to a certain extent only. See, these are the CO2 sinks, plants. Even sea is also CO2 sink. Even land is also CO2 sink. But when I am producing CO2, emitting CO2 in large quantities, which they cannot take up. See, I am not
दूसरे तरीके से बोलता हूँ, ताकि मैं आप ही के सुनता हूँ। हाँ, मेरा आपका कोई झगड़ा नहीं है, पर मैं आपको दूसरे तरीके से बोलूँ। आपसे दिखाया सर 1800 से लेकर 2024 तक 1.6 डिग्री सेंटीग्रेड शायद बढ़ा हो, ठीक है? अगर ये जो बढ़ना है तो 700 साल में एक बार जरूर होता है और वापस चला जाता है। ये आपको कहाँ पता है? मैं आपको इसको दूसरे तरीके से बोलूं, मैं आप सभी के लिए ये बोलना चाहता हूं, क्योंकि देखिए पहले क्या था, पहले डायबिटीज 160 में होता, फिर उसको दवाई बेचना था, बोले नहीं नहीं 140 हो गया तो डायबिटीज हो, फिर बोलते हैं नहीं नहीं 120 हो गया तो। अब ये जो लोग ऊपर बैठे हैं वो अपना बिक्री करने के चक्कर में उसको इधर उधर करके रखे हैं लेवल। नाउ आई एम गोइंग टू माय पॉइंट। आपसे मैं पूछता हूं, अगर आप जोर से छलांग मारेंगे तो आकाश की ओर जाएंगे तो आपको पृथ्वी कैसा दिखेगा? फुटबॉल के जैसे? और ऊपर जाइए, कॉर्क बॉल के जैसे, और ऊपर जाइए, छोटा कंची के जैसे दिखेगा पृथ्वी? क्या आपको पूरे ब्रह्मांड में सिर्फ पृथ्वी दिखेगा? आंसर इज नो, बहुत सारा छोटा छोटा कंची दिखेगा। आर यू गेटिंग मी? अब इतना बड़ा ब्रह्मांड में जहां इतना सा पृथ्वी है, उसमें मेरा और आपका औकात इतना सा है। आर यू गेटिंग मी? और हमारा औकात जो कि इतना सा है, वो इस पृथ्वी का क्या बिगाड़ लेगा? ट्राई टू अंडरस्टैंड। और आगे बोलता हूं, देर आर सेल्फ करेक्टिव मेजर्स। इवन आपकी बॉडी में यदि वायरस ने अटैक किया, फटाक से आपका बॉडी सेल्फ करेक्टिव मेजर्स लेता है। आपको लूज मोशन हुआ, सेल्फ करेक्टिव मेजर्स लेता है। अपने बॉडी में भगवान ने सब बंदोबस्त दिया है कि सेल्फ करेक्टिव मेजर्स लेगा। तो क्या ये पृथ्वी पे सेल्फ करेक्टिव मेजर्स लेने का बंदोबस्त है कि नहीं है? मैं आपको छोटा सा एग्जांपल देता हूं। विंड इज ब्लोइंग फ्रॉम हियर टू देयर, इट इज बिकॉज ऑफ द प्रेशर डिफरेंशियल। तो हवा इधर से उधर दौड़ के क्यों गई? प्रेशर डिफरेंस हुआ। टेम्परेचर डिफरेंस अगर होगा तो हीट फ्लो हो जाएगा। इसका मतलब है देयर आर सम ड्राइविंग फोर्सेस जो इक्विलिब्रियम लाने का कोशिश करता है। आर यू गेटिंग मी? इक्विलिब्रियम। तो अगर कार्बन डाइऑक्साइड से टेम्परेचर राइज होता, अभी सर ने बताया कि 200 मिलीमीटर समुद्र का लेवल बढ़ गया, मतलब 20 सेंटीमीटर बढ़ गया। 20 सेंटीमीटर समुद्र का लेवल बढ़ गया, वो तो ऐसे हिल डुल के एडजस्ट कर देगा। 20 सेंटीमीटर कितना होता है? आपका जो स्केल है वो 30 सेंटीमीटर का है, उससे भी छोटा। क्या मेरे को और आपको इतना चिंता करना चाहिए? इतना बड़ा पृथ्वी में, इतना बड़ा ब्रह्मांड में हम लोग सच में कुछ कंट्रीब्यूट कर पाएंगे? दो साइंटिफिकली द ग्रीन हाउस इफेक्ट में आपका शॉर्ट वेव लेंथ एंट्री करता है, और क्योंकि वो लॉन्ग वेव लेंथ हो जाता है इसलिए बाहर नहीं निकलता, तो ट्रैप हो जाता है। बट माई ओपिनियन इज दैट ट्रैप हो जाता है, देयर इज करेक्टिव मेजर्स। आपको जो टेम्परेचर बढ़ा हुआ दिख रहा है वो 700 साल में अगर एक बार रिपीट होता होगा, मान लो 1.6 डिग्री सेंटीग्रेड रिपीट होता है, और एवरी 700 ईयर्स होता है, तो पीछे का 700 ईयर्स का कोई डाटा ही नहीं है मेरे पास। अभी आगे 700 साल के बाद हमको समझ में आएगा कि साइकिल है कि नहीं है। तो ये जो बहुत जोर जोर से डमरू बजा के अपने को डोमिनेट कर देते हैं, उसको थोड़ा और रिसर्च का जरूरत है। वी नीड सम टाइम, वी नीड टू रीच फ्रॉम साइकिल पॉइंट ए टू साइकिल पॉइंट बी, then only we can prove that yes, it is a cycle and the cycle can be controlled like that. Thank you very much.
Yes, thank you. Thank you for enlightening this house. But मैं थोड़ा सा इसमें कुछ ऐड करना चाहूँगा। ओके, सर ने बोला वेरी गुड कि जैसे हमारा ह्यूमन बॉडी है, नेचर है ना, सेल्फ करेक्टिंग होता है। बट यू फाइंड कि लॉट ऑफ पीपल आर डाइंग बिकॉज ऑफ द प्रॉब्लम्स इन द बॉडी। किसी को कैंसर हो जा रहा है, किसी को टीबी हो जा रहा है, किसी को हार्ट अटैक आ जा रहा है, किसको कुछ हो रहा है, किसको क्यों जा रहा है? वाई द बॉडी इज नॉट सेल्फ करेक्टिंग? बिकॉज वी आर वी आर गोइंग beyond the limit. That's why our body is not able to take care of that. Up to a certain extent, if I do something on my body, body self corrects, no issue. आपको बुखार आएगा, सेल्फ करेक्ट हो जाएगा. लेकिन अगर मेरे को, मैं उसको इग्नोर करता रहूंगा एंड आई डोंट चेंज माय लाइफस्टाइल, आई डोंट चेंज माय फूड हैबिट्स एंड ऑल दैट, तो मेरा बॉडी क्या हो जाएगा? इट विल बी फुल ऑफ टॉक्सिन्स. और फिर मेरे को टीबी हो जाएगा, कुछ हार्ट अटैक हो जाएगा, कुछ समथिंग समथिंग समथिंग, कुछ ना कुछ हो जाएगा. सेम थिंग इज विद द अर्थ. सी, आई एम नॉट लुकिंग फॉर द ब्रह्मांड. ब्रह्मांड इज बियॉन्ड माई इमेजिनेशन, but I am living on earth. 900 crore people are living on earth, and I have to take care of the earth because I am responsible for that. I have to leave my earth as I got it. There are cases, and within 20 years, you see, some of the cities are on the verge of drowning. वो डूब जाने वाले हैं, इतना सी लेवल राइज हो चुका है. सी लेवल राइज जो हो रहा है, ये दैट इज द फैक्ट. ग्लोबल वार्मिंग हो रहा है, दैट इज द फैक्ट. हमारे ग्लेशियर्स मेल्ट हो रहे हैं, दैट इज द फैक्ट. मैं बिल्ली को देख के, कबूतर अगर आंख बंद कर लेगा कि भाई कुछ नहीं हो रहा, कुछ नहीं, कुछ नहीं हो रहा, कुछ नहीं हो रहा, तो बिल्ली आराम से उसका नाश्ता करेगी. ओके, वी हैव टू राइज टू द ओकेजन कि यस, दैट इज द थ्रेट. जो शुगर का एग्जांपल दिया वो ठीक है. वो जो हमारे फार्मास्यूटिकल कंपनीज हैं उनका प्रेशर है, और वो लोग रिवाइज करते रहते हैं. रातों रात उन्होंने लिमिट लोअर कर दिया, तो करोड़ों लोग डायबिटीज के पेशेंट हो गए. ओके, वो उनका प्रेशर है, फार्मास्यूटिकल कंपनीज का. दैट इज देयर इशू. बट दिस इज अ ग्लोबल problem. I cannot avoid the warning signals already given by the nature to me. If I don't correct myself, let it be. Thanks, sir.
Thank you to both, Vishwabandhu sir and Tiwari sir. Though this discussion was not planned, but indeed it was a really fruitful discussion. Thank you to both, sir. Thank you, sir, for sharing the essence of your vast experience, updating us with recent practices and trends in steel industry, and truly contributing to the theme of this conference. After the brief address by Dr. Tiwari for the inaugural session, we now have the opportunity to be the audience to a technical session by him on the topic of energy savings by solar thermal applications. I invite Dr. Tiwari to elaborate on the topic.
यहाँ से गए थे शेयर में, फिर क्या स्क्रीन शेयर करना है? हाँ, स्क्रीन शेयर स्टार्ट नाउ. स्टार्ट नाउ क्या करना है? प्रेजेंटेशन के लिए ये. अच्छा,
है ना, सर ये शेयर किया ना अभी, प्रेजेंटेशन का है, ये है।
नहीं, अच्छा प्रेजेंटेशन शेयर करना, ये 365 अलाउड है।
हाँ, है ना। आप एक बार लॉग ऑफ होइए, फिर रीज्वाइन करिए। एक्चुअली मैक में ये हुआ है।
अस- असली में ना आप परमिट करोगे तब होगा।
हमारी तरफ से फुल परमिट बच्चा।
मेल से जाऊँ क्या वहाँ? मेल से चलो, मेल चलते हैं। लोग रुको 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 रुको, ये वाला है। Yes, sir. लेट गया यार। ये सही है। ऊपर है, ऊपर लिंक, ये है लिंक, ये है लिंक। अच्छा, ये से नीचे वाले। कैमरा को बंद कर दो, माइक को भी बंद कर दो, बस। Right. एक चीज और बंद कर दो, यहाँ का ऊपर का माइक। वो तो मैं बंद कर दूंगा, स्लो कर दूंगा। स्पीकर को बंद करने की बात कर रहा हूँ ना आप, ये करीब। और वहां ओ, ये चीज माइक्रोसॉफ्ट 365 है। ये है फॉर्मेट, क्या इससे करेंगे तो होगा क्या? ये वाला हाँ कर दीजिए इसको भी। कब पैक है? वैसे मैंने उसको चालू तो मैं उससे किया था 365 से। उसको चालू करके देखो पहले चल रहा है कि नहीं। वापस उस पे ले जा रहा है। यही तो स्क्रीन है यहाँ पे।
365 को ही करिए सर।
ये देखो, ये है। वो तो चालू बंद कर दिया आप। ये देखो यहाँ पे, ये इसको चलाता हूँ। ठीक है, मैं देता हूँ।
ठीक। अरे मैक में इशू आता ही है यार, इसको लॉग ऑफ नहीं।
आगे वो दिखा, वो पॉइंटर सर। आगे स्लाइड कैसे चेंज होगी? स्लाइड कैसे चेंज होगी? ऐसे उधर वाला उधर। Mic. So mic. Okay.
डियर फ्रेंड्स, मैं जिस टॉपिक पे बात करूंगा आपसे, मैं ज्यादा से ज्यादा लोगों को तक ठीक से पहुंचना चाहता हूं, इसलिए बीच में हिंदी बोलता हूं, अपनी क्लास में भी बोलता हूं। माय टॉपिक इज रीसेंट ट्रेंड्स ऑफ एनर्जी सेविंग बाय सोलर थर्मल एप्लीकेशन। इसमें मैं 4 केस के बारे में बात करूंगा, लेकिन 13 हो चुका है और मैं सिर्फ 20 मिनट बोलूंगा। उसमें अगर एक केस हुआ तो ठीक, 2 हुआ तो ठीक, 3 हुआ तो ठीक, या चारों हो गया तो ठीक। बीच में मैं रोक दूंगा किसी एक केस को कंप्लीट करके। तो इन कमिंग अबाउट हाफ एन आवर, द अबाउट टॉपिक इज एक्सप्लेन्ड बाय 4 केस स्टडीज, जो मैं आपको बता चुका हूं। हाफ एन आवर नहीं बोलूंगा, चिंता न करें। सबसे ज्यादा जो सोलर एनर्जी का बेनिफिट है, वी नॉर्मली एंजॉय सोलर एनर्जी बाय द हीट ऑफ द रेडिएशन, और उसी हीट ऑफ द रेडिएशन से हम बहुत सारी चीजें कर सकते हैं, इन विच द कूलिंग इटसेल्फ इज कंसर्न। वी कैन कूल आवर होम बाय यूजिंग द हीट ऑफ द सोलर रेडिएशन इवन। ओके, सो द केस स्टडी, द सोलर वाटर हीटिंग एप्लीकेशंस हम देखेंगे, जो कि बहुत पहले से आप जानते हैं। वाटर डीसैलिनेशन बाय सोलर ह्यूमिडिफिकेशन एंड डीह्यूमिडिफिकेशन। नॉर्मली नॉर्मली सोलर डिस्टिलेशन के केस में हम वाटर को गर्म करते हैं और फिर वेपोराइज करते हैं और फिर कंडेंस करते हैं। लेकिन जिस टेक्निक पे मैं बात करूंगा आपसे, देयर द वाटर विल नॉट बी हीटेड, एयर विल बी हीटेड। मैं आपको छोटा सा एक हिंट देना चाहता हूं। अगर आपके पास एयर 22 डिग्री सेंटीग्रेड की है, उसकी जो वाटर कैरिंग कैपेसिटी है, वो विथ कंपैरिजन टू 44 डिग्री सेंटीग्रेड की एयर की कैसी होती होगी? आपके दिमाग में आंसर होगा, मैं आंसर देता हूं आपको। द वाटर कैरिंग कैपेसिटी ऑफ हायर टेम्परेचर एयर इज ऑलवेज मोर। वाटर कैरिंग कैपेसिटी बढ़ने का मतलब होता है वाटर कैरी करने वाला झोला बड़ा हो गया। एयर वही है, टेम्परेचर कम झोला छोटा, टेम्परेचर ज्यादा झोला बड़ा। बस इसी टेक्निक को हम यूज करते हैं, राइट। सोलर चिमनी फॉर कूलिंग एंड वेंटिलेशन। चिमनी आपने पढ़ा होगा, चिमनी इज क्रिएटिंग अ प्रेशर डिफरेंशियल बिकॉज ऑफ द प्रेजेंस ऑफ हाइट, एंड दैट प्रेशर डिफरेंशियल लीड्स टू द फ्लो ऑफ द एयर। Once there is a flow that has been maintained because of the height of the chimney, there will be a continuous flow. आपने कुछ बिजली खर्चा नहीं किया, पर एयर फ्लो हो रही है। Now, how it is possible? It is possible because of the pressure difference created. Normally, where it is created? It is created in chimney. So, I will be talking about solar chimney. Solar metallic wall for ventilation and heating. आपकी दीवार नॉर्मली मैसनरी की होती है, लेकिन बाहर की तरफ जिसके ऊपर सूरज गिर रहा है, वहां अगर आपने मेटल लगा दिया, तो उस मेटल को तो तपता हुआ गर्म कर सकते हैं आप। और एक बार अगर वो गर्म हो गया, तो यू कैन एंजॉय लाइक एनीथिंग व्हाट एवर यू वांट टू डू, दैट आई विल बी डिस्कसिंग। ओके, इसके अलावा और भी चीजें होती हैं, जैसे आप देखेंगे सोलर ट्राम वॉल, स्पेस हीटिंग एंड कूलिंग बाय सोलर ट्रांसपायर्ड वॉल, सोलर पैसिव एंड एक्टिव डिस्टिलेशन। इन सारी चीजों के बारे में जो यहाँ 3 लिखी हुई हैं, आज के टॉक में मैंने शामिल नहीं किया है। ये पहला केस है जिसमें आप देखेंगे टेक्नो इकोनॉमिक एनालिसिस ऑफ यूजिंग सोलर एनर्जी थ्रू वाटर हीटिंग एप्लीकेशन फॉर रायपुर सिटी, स्टेट कैपिटल ऑफ इंडिया। इसमें हम लोगों ने जो पॉपुलेशन लिया है, वो 2011 में जो रायपुर की पॉपुलेशन थी, उसको कंसीडर करके लिया है। ठीक है, आप अगर ध्यान से देखें तो रायपुर के बारे में जानकारी दी है, लैटिट्यूड, लॉन्गिट्यूड, क्लाइमेटिक जोन, पॉपुलेशन, एवरेज नंबर ऑफ पर्सन पर फैमिली। ये इमेजिन किया है, बाउंड्री कंडीशंस। हमने इमेजिन किया कि 6 परिवार में 6 आजकल तो नहीं होते हैं, लेकिन जब मैं था यंग, तब कम से कम 6 लोग एक परिवार में होते थे, तो इसलिए मान लिया 6 आदमी है एक परिवार में, मतलब एक घर के अंदर। Hence the number of family, that is household, मतलब कितने घर होंगे अगर इतना पॉपुलेशन है, तो ऑलमोस्ट 2,50,000 घर आपको दिखते हैं। अब अगर आप देखें, अब पूरे पूरे रायपुर में प्राइवेट घर भी बने हुए हैं, पर सैंपल स्टडी के लिए मैंने मान लिया कि छत्तीसगढ़ हाउसिंग बोर्ड जितने घर बनाया है, उस घर को ही अगर मैं कंसीडर करूं, कितना उत्पाद बाहर निकल के आता है, राइट। तो उसके पास जो घर है वो LIG है, MIG है, HIG है। HIG मतलब हाई हाई इनकम ग्रुप, उनके पास पैसा ज्यादा है। MIG मीडियम, LIG लो इनकम ग्रुप। तो आप किसी भी सोलर अप्लायंसेस के लिए अगर कन्विंस करने जाएंगे LIG, MIG और HIG को, तो कौन सबसे ज्यादा कन्विंस होगा? जिसके पास थोड़ा पैसा ज्यादा है। HIG का कन्विंसिंग ज्यादा होगा, MIG का थोड़ा कम और LIG का थोड़ा और कम। यहां पे मैंने स्लाइड में दिखाया है एज फार एज द परसेंटेज ऑफ इलेक्ट्रिसिटी कंजम्पशन। तो आप देखेंगे कि जो मैक्सिमम है वो वाटर हीटिंग में है और जो मिनिमम है वो आपके किचन इक्विपमेंट में है। अब वाटर हीटिंग में हम क्यों करना चाहते हैं, ध्यान से देखेंगे तो मैक्सिमम जो है इट इज फॉर बेथिंग और मिनिमम जो है फॉर द किचन वॉशिंग। ये छोटा सा एक आपको दिमाग में क्लियर रहे कि कहाँ पे गर्म वाटर मेरा जा रहा है। नाउ हियर हॉट वाटर इक्विपमेंट फॉर ए टिपिकल हाउस होल्ड, ये यहाँ पे सेम चीज दी है लेकिन टेबल के फॉर्म में दी हुई है, राइट, जो आपने चार्ट के फॉर्म में देखा था। अब दिस स्लाइड इज शोइंग यू अबाउट द सोलर रेडिएशन। आप देख सकते हैं वाई एक्सिस पे डेली सोलर रेडिएशन इन किलोवाट पर मीटर स्क्वायर पर डे, ध्यान रखिएगा पर डे फॉर द होल डे दिया हुआ है। तो आप देख सकते हैं नीचे नीचे जनवरी, फरवरी, मार्च अप टू दिसंबर, आप देख सकते हैं जुलाई से लेकर अगस्त, सितंबर इसका डाउनफॉल है। अब यहाँ दो ग्राफ क्यों है? वन ग्राफ इज शोइंग यू विच इज टिल्टेड, अनदर ग्राफ इज शोइंग यू विच इज हॉरिजॉन्टल। ओके, तो ये सोलर रेडिएशन के बारे में एक अंदाज है। द हॉरिजॉन्टल सरफेस रिसीव्स मोर इन द ड्यूरेशन फ्रॉम, ये तो कॉमन सेंस भी है, अप्रैल टू सितंबर, एंड ड्यूरिंग अदर 6 months tilted receives the more. Now what is the optimum tilt angle? तो ऑप्टिमम टिल्ट एंगल अगर मैं आपसे पूछूं तो हर महीने का अलग होगा। अगर मैं सीजन की बात करूं तो हर सीजन का अलग होगा। अगर मैं एनुअल की बात करूं तो एनुअल का अलग होगा। तो आप किस पर्सपेक्टिव में ऑप्टिमम एंगल निकाल रहे हैं वैसा आपको आंसर मिलेगा। यहाँ पे जो वैल्यूज दिखाई हैं वो देखिए 1 2 3 4 चार के लिए दिखाई हैं, जिसमें से मुझे पता है और याद है कि दिस वैल्यू इज फॉर, दिस एंगल इज वेरी सुटेबल फॉर समर एंड दिस एंगल इज वेरी सुटेबल फॉर विंटर एंड दिस एंगल इज वेरी सुटेबल फॉर ईयर अराउंड। आपको बार बार चढ़ के अगर चेंज ना करना है तो यही चीज लिखी है यहाँ। यहाँ मैंने आपको पहले बता दिया है समर का 6.2 दिस, जुलाई टू अक्टूबर दिस, एनुअल दिस, ये ऑप्टिमाइज्ड वैल्यू है एंगल की ना। ऑप्टिमाइज किसके लिए? फॉर रिसीविंग सोलर रेडिएशन। अब देखिए इस ग्राफ में बहुत अच्छा एक इंफॉर्मेशन है आपको। नाउ सी, अगर आपके पास ठंडा पानी 25 डिग्री सेंटीग्रेड का है और आपको मिक्स वाटर 45 डिग्री सेंटीग्रेड का चाहिए, तो 55 डिग्री का गर्म पानी कितना लगेगा, 60 का कितना लगेगा, 70 का कितना लगेगा, 85 का कितना लगेगा, 90 का कितना लगेगा। तो आप देख सकते हैं कि 90 डिग्री का है अगर, तो क्वांटिटी ऑफ हॉट वाटर इज लेस। अगर क्वांटिटी ऑफ हॉट वाटर इज लेस, इसका मतलब है आपका सोलर फ्लैट प्लेट कलेक्टर का साइज आप छोटा कर सकते हैं, कॉम्पैक्ट कर सकते हैं। इसका क्या मतलब हुआ? इफ यू हैव स्मॉलर एरिया ऑन द रूफ, आपका जो डिजाइन होना चाहिए वो बहुत ही कॉम्पैक्ट होना चाहिए, और दैट टू जिसमें कि टेम्परेचर 90 तक पहुंचे या 85 तक पहुंचे। इसका देखिए दोनों का सेम है। ये आप, दिस इज जस्ट आपके दिमाग को खोलने के लिए ताकि कैसे आप सोच सकते हैं, एक रिप्रेजेंटेटिव ग्राफ है। ओके, अब ये अगर मैं कहूं कि 45 नहीं, 45 चाहिए लेकिन ये 20 का है, अगर मैं कहूं कि नहीं ये तो 15 का है, अगर मैं कहूं नहीं ये तो 10 का है, तो अलग अलग ग्राफ बन जाएंगे, आप निकाल सकते हैं। मेनली ये बात मैंने बता दी जो लिखा है, if the capacity of solar water heat is lower then the size and the space required will be lower। ये देखिए 20 का है और 45 चाहिए, तो ये ग्राफ है, रिपीटेशन ऑफ ग्राफ है आइडिया के लिए। अब ये मेरा मेन इंपॉर्टेंट टेबल है जो आपको इंफॉर्मेशन देता है कुछ, ध्यान से देखिए। अगर अगर LIG में इतने घर हैं और 10% भी मान गए, मतलब 532 भी घर मान गए आपकी बात, तो हमारा इतना किलोवाट आवर सेव हो। MIG में 30% मान गए, क्योंकि जैसे जैसे पैसा बढ़ते जा रहा है पैसे वाले लोग होते जा रहे हैं तो उनको कन्विंस करना आसान है। ओके, अगर मैंने सभी को कन्विंस कर लिया तो दिस इज नोन एज ऑप्टिमिस्टिक सिचुएशन। और अगर मैंने सिर्फ 10% को किया, 30% को किया और 45% को किया, दिस इज नोन एज पेसिमिस्टिक सिचुएशन। मैंने दोनों सिचुएशन में आपको क्या बचा, क्या खोया, क्या पाया बताया है। देखिए, अगर पेसिमिस्टिक सिचुएशन है तो आप टोटल इतना पावर बचाएंगे इलेक्ट्रिसिटी का, जिसमें इतना रुपया बचेगा पेसिमिस्टिक कंडीशन में। लेकिन अगर सभी को आपने कन्विंस कर लिया तो आपका इतना पावर बचेगा और इतना रुपया बचेगा। अगर आपने ये नेट एनुअल ग्रीन हाउस गैस एमिशन रिडक्शन पर इंस्टॉलेशन इज 3 टन्स ऑफ कार्बन डाइऑक्साइड एवरेज, ये एनुअल वैल्यू है। ओके, अगर आपने पेसिमिस्टिक मतलब कम लोगों को कन्विंस कर पाए तो इतना टन ऑफ कार्बन डाइऑक्साइड एटमॉस्फेयर में नहीं जाएगा। अगर आपने सभी को कन्विंस कर लिया तो इतना नहीं जाएगा। तो आप ये सोचिए, मैंने सिर्फ छत्तीसगढ़ हाउसिंग बोर्ड की बात की है, तो अगर सभी घर को मैं इनकॉर्पोरेट करूं तो मैं कितना बिजली बचाऊंगा, कितना रुपया बचाऊंगा और कितना टन ऑफ कार्बन डाइऑक्साइड को एम्बियंट में जाने से रोकूंगा। राइट, तो दिस वाज द फर्स्ट केस स्टडी। यू कैन सी दैट कि पर ईयर एक फैमिली कितना बचा रही है, एलआईजी वाली पर ईयर इतना, एमआईजी वाली इतना, एचआईजी वाली इतना, ये सब रिप्रेजेंटेटिव वैल्यू है। मैंने एक वैल्यू जितनी बिजली का चार्ज था उसके हिसाब से लिया है। बिजली का चार्ज बढ़ता घटता रहता है, ठीक है, बिजली वाला एंगल हो सकता है फ्री कर दें, इसलिए बोला। तो ये सब रिप्रेजेंटेटिव वैल्यू है। कॉस्ट ऑफ इंस्टॉलेशन, यहाँ पे टेंटेटिव कॉस्ट ऑफ इंस्टॉलेशन है, जिसकी मदद से आप ये देख सकते हैं। देखिए, ध्यान से देखिए, एनुअल फ्यूल कॉस्ट, फ्यूल से मेरा मतलब इलेक्ट्रिसिटी से। आप देखिए, हायर टेम्परेचर के लिए ज्यादा बिजली लग रही है, लोअर टेम्परेचर के लिए कम बिजली लग रही है। दिस ग्राफ इज रिप्रेजेंटिंग एंड क्लियरली शोइंग यू द पे बैक पीरियड ऑफ फ्लैट प्लेट कलेक्टर। आप देख सकते हैं, जब टेम्परेचर ज्यादा मुझे प्रोड्यूस करना है हॉट वाटर का और इस बिजली को मैं बचाता हूं तो पे बैक पीरियड सबसे कम है, अदरवाइज पे बैक पीरियड ज्यादा है अगर मैं हॉट कम गर्म करता हूं विद द हेल्प ऑफ इलेक्ट्रिसिटी। तो सिमिलरली दिस वैल्यू इज, this is for evacuated tube, right? And this is what net annual reduction in greenhouse gases. ये आपका हो गया evacuated tube से, ये आपका हो गया flatted से। So this way you can analyze and you can reach to the decisions. Now the case 2, इसमें need for new fresh water resource. Okay, right. I am going to talk about how to use solar energy for making potable water. Okay. You can see that you see here, air from the ambient is entering. This is cool air. Here it is glass. Now air is traveling one pass, then two pass, right? When it is traveling from one pass, then two pass, it is getting heated. When it is getting heated, it is being allowed to enter a humidification chamber. Now in humidification chamber, the salinated water, brine water, is actually sprayed over. Since air is heated, its water carrying capacity is very high. It carries the water of the order of RH is 100. Then it goes to a heat exchanger where this air, which is of course heated, later on it is carrying the full amount of water vapor is being cooled by the cool water available in the atmosphere. And this way you can collect fresh water here. So this is very simple. There is no energy needed. Only one place you need energy is pumping water to spray. That's all. But you can create pure water. Now, बाकी यहाँ जो लिखा है वो that I have already explained. These are the, for mathematical modeling, the equations, these are required, not necessary to be told here. You can refer it in the book or in the papers that has been published. Program and how to, these are the assumptions, this value has been taken for analysis. Now, here is the information. अगर आप ध्यान से देखें तो higher the temperature after solar air heater, point number 1, and lower the temperature after the dehumidifier. ऐसे दिखाओ कि समझ में। Right. These temperatures are very important. जितना ज्यादा एयर हीटर के बाद एयर का टेम्परेचर होगा उतना ज्यादा वो वाटर कैरी करेगा। सिमिलरली जितना लोअर ह्यूमिडिफायर से निकलते वक्त एयर का टेम्परेचर होगा उतना ज्यादा वो अपने अंदर से पानी छोड़ेगा, इस तरह उतना ज्यादा एक्सपेंशन होगा। So these two temperatures are very important. This is the reason why I am talking on only these two temperatures. You can see that here humidifier outlet temperature और दूसरा टेम्परेचर क्या है, dehumidifier outlet temperature. You can see that as the mass flow rate of the air is increasing up to 0.03, the temperature, outlet temperature is continuously decreased. इसका मतलब है कि as an engineer you must have to reach a optimum mass flow rate. क्योंकि अगर मास फ्लो रेट को बहुत छोटा कर दोगे आप तो यहां रहेगा टेम्परेचर पर क्वांटिटी इतना कम रहेगा कि क्या कितना वाटर कैरी करेगा. You must have to what? Optimize it. So here the optimization say tells about this way. इससे ऊपर बढ़ाने का कोई मतलब नहीं है. Okay. Sharp drop, 80% drop up to the flow rate of this. Now what is drop? Where? Drop in this temperature. Okay. And this is a humidifier outlet temperature. You see, now here humidifier outlet temperature is being talked about. You can see that it is increasing with the initial temperature of the water. जो वाटर आपके पास है और आप ये अच्छे से जानते हैं the water which is being continuously sprayed उसका टेम्परेचर क्या हो जाएगा थोड़ी देर के बाद, वेट बल्ब टेम्परेचर जैसे कूलर में होता है. राइट. इसका मतलब है वो किस तरफ रहेगा. अगर मैंने 40 पे भी डाला है वाटर को तो वो थोड़ी देर के बाद इस दोनों के बीच में रहेगा. राइट. सो दिस इज इंफॉर्मेशन. Here dehumidifier outlet temperature, you can see that it also depends on initial temperature of the water. Now significant dehumidifier outlet temperature जो है इसमें ड्रॉप हुआ significant कब, किस मास फ्लो रेट में, कूलिंग वाटर का मास फ्लो रेट जब 0.045 था. Okay. So what I want to say, by doubling the air heater area, the outlet temperature from humidifier and dehumidifier can be increased by 72%. This value is coming by the analysis. This increases ultimately affects the yield positively. That will be more clear in coming graphs. देखिए ये double pass, single pass, if there is no air heater, you can see that the difference in the output 5.5 kg per hour, 4.5 like that. Okay. Now, the above result shows the superiority of the double pass solar air heater over the single pass solar air heater, particularly for proposed desalination system. You can see here, it is maximum here. जो हमने पहले ही डिसाइड किया था, एयर का मास फ्लो रेट यही मेंटेन करता है. राइट. It is clear up to the optimum mass flow rate of 0.03 kg system gives a 400% increase in productivity with 200% increase in air mass flow rate. After that, even with 70% increase in the mass flow rate over the optimized value, 40% decreased productivity can be observed. तो हमेशा mass flow rate बढ़ाना फायदेमंद नहीं होता. Right. So this I have already explained. This is conclusion. I have already, in other words, I have told you already. Now highlights. Operation at low temperature is possible. Ability to utilize sustainable energy sources, that is solar and geothermal, and require. अच्छा, एक बात और बताना चाहता हूँ. एयर को गर्म करने की बजाय यदि water not having some of the geothermal energy or you can spray them. It will be more evaporated. So you can play with that. Requirement of the low technology level by increasing the area of the solar air heater, we can increase the yield to the desired level. In this arrangement, solar metallic ball, right? This is third one. I think I could stop here. There are two more cases, so I can explain next time. Thank you very much.
Thank you very much, sir. So thank you, sir. Your insights into the energy savings will surely motivate our audience to strive to adopt the solar energy technologies for better saving. So moving next, we have with us another eminent speaker from academia. Please welcome Dr. Chandrakant Nirala. He is joining us virtually.
Yeah, hello, good afternoon. I'll just share my screen. Please confirm if it is visible to you and I'm audible to you.
Yes, sir. It is visible and you are also audible, sir.
Okay, thank you. Good afternoon. Shall I go ahead?
Yes, sir.
Okay, thank you. Good afternoon. This is Chandrakant Kumar Nirala. I'm Associate Professor in the Department of Mechanical Engineering at IIT Roper. The title for the today's discussion is the current and future research trend in spark erosion based machining process. In this, I'll be particularly highlighting the novel applications of micro electrodischarge machining for innovative products. So I just wanted to minimize the, yeah. Okay. So a brief introduction about my research lab. Our research lab, it's called a Micro Machining and Monitoring Lab. It is situated in the Department of Mechanical Engineering, that is Satish Dhawan Block, IIT Roper. So the history of this lab is very short. It's not very old. Since I have joined here in 2017, I established this lab in 2018. And since then, we have 3 PhD students graduated and 2 have submitted the thesis and 4 is ongoing. And we have 2 part-time PhD ongoing. And then up to 15 MTech projects completed from this laboratory. These are the few equipment that we house in this particular lab, research lab. It consists of a multi-purpose micro machining setup of a micro tool make DT110i model, which has the capability of carrying several conventional and non-conventional machining processes at micro scales. And we have another machine here. Let me just open the ledger pointer. So we have another similar type of tabletop machine. It is also a multi-purpose micro machining setup, and both the machine, this one and this one here, have the capability to handle the positional accuracy of up to 0.1 micrometer. We have the data acquisition system of 2.5 gigasample sampling rate. It can acquire the data from a current, voltage, and for temperature, for humidity, for acoustic emission, and other few equipment such as micro weighing balance. We have the contact angle meters and Isler mini dynamometer. It is under procurement. So let us move ahead with the microsystem technologies. Okay. So see, whenever we talk about any micro fabrication technology, in my opinion, we must know about the microsystem technology. Microsystem technology basically have their characteristic as the miniaturization, which is essentially the devices or the system that is designed to be compact, lightweight, and at the same time without compromising the efficiency of the system or the devices. Then there is integration. So once we have the miniaturized devices, then it must go under integration to make a complete system. And then there comes the precision. Precision whenever we have the miniaturized device and integrated to a system, precision is something to achieve a high level of positional accuracy and functionality at small scales. And in order to miniaturize the component, to integrate them, and to achieve the positional accuracy, we must talk about the materials. So in the microsystem technology, the materials ranges from, for example, silicon to polymer to ceramic to metals. So for an example, here we can see the two images of uh, ratchet mechanism, and another one is the microchain system. Here we can see how the miniaturized devices or the parts are integrated together to make a system. Here in the microchain drive system, we have the disk housing the chain of diameter. We can see this is the scale bar of 100 micrometer. So approximately 200 micrometer. In this, the chains are clubbed, and the chains are of a combination of a number of elements. Each element size is approximately 15 to 20 micrometers. Just you can imagine the size. So just for a reference, the human hair thickness is approximately 40 to 60 micrometer. And this element size is 15 to 20 micrometer. So it cannot be visualized from the naked eye. Such a system can be fabricated and can be integrated to achieve the miniaturized system with the high precision. Materials, of course, can be of polymer or silicon in this case, or in fact the metals. So we can now say that the microsystem technology is an interdisciplinary field of research which focus on the design, development, and application of the small scale systems and device that integrates various components such as sensors, actuators, microelectronics, and mechanical structures. So we must be wondering about the scales. So from where the microsystem technology starts and what is the upper range of the microsystem technology? Technology that consists of handling the material to fabrication to developing the device and designing the device and integrating it into the system. So all this has a various scales. So the scale of microsystem technology starts from an angstrom to a few nanometer. For example, here 1 angstrom to 10 nanometer. It is the size that is actually the atoms, molecules, and viruses can be classified. And the technology that handles such range is called the nanotechnology. And how can we observe those components? So we require to have the electron beam microscopy or SGM for that. And the fabrication methodology for those components are the nanofabrication processes. Similarly, we have the scale in the micro scale starting from 1 micrometer to up to 100 micrometer that can be characterized as the microsystem technology, where we talk about the parts like bacteria and human hair. And it can be observed using the optical microscopes, and the technologies that uses at that scale is the silicon layer processing. That is something like lithography is a one part of that. Then the chemical oxidation, thermal oxidations, CVD, PVD, what we know. So all comes under the microsystem technology. That is the ranges from 1 micrometer to 100 micrometer, a round figure. Fine. And here the precision engineering is somewhat 10 micrometer to 1 mm, but precision engineering essentially doesn't mean that the accuracy at that scale, rather it is the component at that scale. So accuracy can be much lower than that. Maybe somewhat 1 micrometer or even lesser than that, 100 nanometer. So this precision engineering is the component of a size of 10 micrometer to like 1 mm, maintaining the accuracy of lesser than 1 micrometer. Then there comes the traditional scale of engineering, where we do the processes such as conventional machining processes or casting, forming, or other metalworking. That can be observed using the magnifying glasses or the naked eyes. So this is the microsystem scales. Now, based on the today's topic, we are supposed to discuss about the microfabrication processes. So the microfabrication processes are classified broadly as the silicon layer processing, the Liga process, and the other micro manufacturing techniques, where we have the classification of non-conventional and conventional process at micro scales. So how can we differentiate these other micro manufacturing techniques than the SLP and the LIGA? It is the process. Other micro manufacturing processes are those which do not require any substrate or selective etching or the material removal. We directly go for the tool-based material removal. It can be conventional or non-conventional source of energy. So the today's discussion is on the novel technique for fabrication of micro pin fins using micro EDM for heat management applications. That heat management applications can be in the microelectronic components where we have the high heat flux on the surface of any high performance microelectronic, that heat needs to be immediately dissipated to save the component from its failure. So our step is just to take care of the heat generated or the high heat flux generated over the hot surface to the environment through the micro pin fins by novel design of micro pin fins that is fabricated using micro EDM, and that is the technique for the heat generation, heat dissipation through the conventional way, or we can say the passive heat dissipation technique. And other applications that I wanted to highlight is the sustainable machining. Sustainable machining means the machining processes, for example, the turning operation at micro scale, do require the research over the tool surfaces so that we can minimize the heat generation and hence the failure of the component, tool, workpiece, or the surface deterioration. So one step towards that is to generate some novel textures over the rack surface near to the cutting edge so that we can passively dissipate the heat from the cutting zone. So we'll be able to look into that. So this is the first thing that we will talk about, the novel technique for fabrication of micro pin fin for heat management applications. And this fabrication is through micro electro discharge machining technique. So in this figure, we can see a laser micro machining setup is attached with the DT110 micro machining tool, multi-purpose micro machining tool. And here the laser is in operation to create some kind of arrayed micro holes over the tool plate, or plate, which is called as tool plate in this case. And the process is actually the reverse of the state polarity EDM. We call it as the reverse micro electro discharge machining. And here, after fabrication of those micro pin fin heat exchangers, although we are not able to visualize that here, we will be seeing it in the later slides. This is the testing setup for the heat dissipation. We have the ammeter, we have the voltmeters, we have the test rig fabricated here, the acrylic one test rig, where we have the inlet and outlet air, and to monitor that we have the detegration system. And here we can see the drop and the pressure, change in the Nusselt number, change in the Reynolds number, etc. And we can define a new term called the thermal performance index of a particular type of infinite exchanger that we have proven. So the objective of this particular research was to develop the technique for fabrication of arrayed micro pin fins and improving the quality of those pin fins by ultrasonic assisted micro EDM. I will show you that how the simply reversing the polarity doesn't work very accurately. We get some deterioration in the dimensional accuracy of the pin fins. So we need to assist the process with some additional energy. Here we have done it through the ultrasonic machining. There can be several other techniques like improving the flushing technique, improving the or controlling the discharge gap so that we can achieve maximum number of normal discharges and hence the normal removal of the material. Normal means the every discharge removes the material from its maximum capacity. Then we will go for the numerical modeling and simulation for heat dissipation for the various applications. So this I wanted to show you in the brief. So I was just talking about the novel pin structures. Just imagine surface of a metal, a flat surface of a metal have the protruded structure of these many shapes: droplet, elliptical, piranha shape, hexagonal, cone, hydrofoil, and some similar other shapes. Then, and the hot air is allowed to inlet from one particular direction and allowed to exit from the another one. So you can get the maximum surface area and at the same time a very smooth pressure drop so that we can ensure a better performance of the heat exchanger. So this particular figure shows the techniques for fabrication of the arrayed micro pin fins. These were able to see the figure C. Here, this is the metal plate. It can be any metallic plate. We have used here as a brass and copper plates and steel also. For an instance, the elliptical holes are prepared using laser micromachining. The hole size is of some 250 to 250 in the minor axis and some 500 into the major axis. Sorry. These array of elliptical holes are fabricated over a thin film of metal, which is used as a tool plate for the reverse EDM process. The schematic of that can be seen here. And if you use a bulk material attached with the spindle without rotation and bringing them closer within a tank of electro discharge machining, having filled with the dielectric material, there are pins supposed to get generated over the bulk material. It means the material removal from the anode will take place. We have made this bulk material as anode and the plate as cathode. So we will be having such kind of array of micro pillars or micro pins, or you can say the micro protrusions. Here we can see the example of that. These are the actual real picture of those fabricated micro pin pins. So these two figures, figure A and B, shows the arrayed micro holes that is used to fabricate this particular structure of elliptical shape. So initially we can see the here it is before machining, and after machining what happens, there is certain amount of tool wear. Here we call it as the tool plate wear, and subsequently it fabricates the arrayed micro structures. We can see here. For other microstructures, we had used a similar pattern of micro holes like we used for the elliptical aerofoil case here. For elliptical, pyramid, square pyramid, piranha, and the water droplet, we used a similar pattern of micro holes as we have used for the aerofoil here. Here we can see the damages of the wall. We call it as the dimensional inaccuracy. Here, the zoomed view, we can see this wall has got deteriorated. Similarly, the nose of this particular aerofoil structure has got deteriorated. So we were worried about two things. Let me see if it is there. Yeah. So we were worried about two things here, that the time taken in machining, one particular array of 20 by 20 took us some 7 to 8 hours for machining. And at the same time, we got the defects in the dimensional accuracy. We got defects in the walls. How to resolve that? So as I mentioned, there can be several ways. One we tried is the flushing, that is not mentioned here. Improving the flushing, that is basically the suction technology. Another one, what we did is the development of retrofittable ultrasonic vibration setup for the micro EDM, and that significantly improved the result. By machining time using that technique was reduced by 48.22% in a particular case. We can see here the machining time, how it decreases with increase in the frequency of the ultrasonic vibration. So we operated basically on the 100 Hertz and 150 Hertz. So we were able to achieve the better machining time, that is the reduced machining time for the fabrication of one particular array. Here, this is the retrofittable setup. This is the CAD drawing of that, and this is the actual setup we developed. And this is basically vibrating. This is a eccentric motor inside that, and it is vibrating and providing a longitudinal vibration to the tool. And that is basically providing clearance to the discharge gap and a better debris removal, and thereby and fabrication time is reduced. So we just wanted to analyze at the microscopic level that what is happening with the various parameters of the electrodischarge machining to the plasma. Here we can see in this picture that we have the various plasma dimensions captured at the varying capacitance. Here the capacitance at the last one is used is 100 nanofarad for a single discharge. Here in this it is 1 nanofarad, and in between we have the 10 nanofarad. So increases the energy. I don't have the picture of this varying plasma diameter for the ultrasonic vibration case. So that what we observe that 15 to 20% of the spark intensity increases once you have the ultrasonic vibration incorporated into a particular process operating at a particular parameter. So the effect of ultrasonic vibration can also be visualized from here, that the discharge pulses increases in this particular figure. If you see, the discharge pulses has increased by a certain extent, that is the 90.07% of the normal discharges started occurring when you use the ultrasonic vibration to this, or sonic or ultrasonic vibration. The aim is to keep the discharge gap dynamic. And so similarly for the other parameters also, we were able to see a significant improvement in the discharge pulses, percentage of the discharge pulses. And at the same time, we were able to achieve the improved material removal rate with vibration in any particular case. If you see that, for example, the material removal rate with vibration is this gray color line at the different capacitance and feed rate. Similarly, if you don't have any vibration into that, so this is the material removal rate. So we were able to significantly improve the material removal rate, sometimes up to by 50%. And the microscopic analysis of the product we saw that the tool wear, sign of the tool wear in this picture, you can see that has decreased if you use the vibration. So the tool wear from the circumference was 362 micron, which reduced to 265 micron in the same case. Have the ultrasonic vibration, and tool wear was also reduced. To identify the tool wear, because tool wear, if there is a tool wear in any case of electrodischarge machining, it will compromise the dimensional accuracy of the product. So here you see the product. For the same machining parameter and for the same duration of machining, with the ultrasonic vibration, we got 295 micrometer of depth, whereas it was 202 without vibration. It means there was a significant amount of tool wear that has compensated this height of the machining. And the microscopic craters, if you see, the craters are more clean here. There is no sign of debris or carbon particle, because carbon particles that comes from the hydrocarbon fluid dielectric, there is no sign of that. It means there is a proper debris evacuation that actually leads to the occurrence of the normal discharges more frequently. Here we can see the ultrasonic vibration assisted microelectrodischarge machining produces a thin layer of the recast zone. So these are the sign that why we are getting a better result. So we can have evidence through these images. This is the optical microscopic image. So earlier we saw the carbon particles attached. Here we can see it in the colorful image. So there is a clear sign that with vibration we do not have this kind of contaminations on the surface, whereas it is there in the case of without vibration. Regarding surface finish is also significantly improved using the ultrasonic. Yes, please.
Sir, am I audible?
Yes, yeah.
Sir, there is a small request. Sir, can you please find up quickly as we are running short of time? Sorry for this, sir.
Sure. Okay. So this is the surface finish. You can see improved in the surface finish. This is the dimensional finishing. You can see after implementation of the ultrasonic vibration to the microelectrodischarge machining, how sharp the edges are now. Another application what I was talking about, heat dissipation for the electronic component. This is the control volume, this is the thermal model, and we can see the thermal performance index of those arrayed micropin fins are much better than the others when we use the piranha shape of pin fins. Another application is, as I mentioned in the beginning, that we can have such kind of arrangement at near to the cutting edge on the rack surface for the better dissipation of heat in a turning operation. So this is the actual image of those pillars. We have made the circular pillar in order to keep the symmetric about these axes. And this is the improved temperature heat dissipation through the temperature measurement in from a test rig. And if we have such kind of structure, it gives the better curling of the chip and chip breakage, so that it cannot prevent the machining further. You can see the less amount of adhesion of the material as compared to the without or the plain tool. This is the tool wear, sign of the tool wear. That also improves the tool life if you have the textures over the surface. This is the thermal modeling. And now I'm concluding this. The conclusion tells you about the successful development of a technique for fabrication of wired micropin fins, successful implementation of the ultrasonic vibration to that improves the MRR by 35% in general and improves the normal discharges by 90% in general. Materials like tungsten carbide were able to get machined through these textures, whereas it was not able to get machined through the plane tool in the turning operation, conventional turning operation. And low depth of texture in contact region reduces the contact area, whereas high depth texture beyond the contact region enhance the heat dissipation in turning operation. So this was all about my presentation. Thank you very much. So am I audible?
Yes, sir, you are clearly audible. Any questions
So
from
if there
audience?
is-
Yes.
Sir, I'm audible.
Yes, you're audible to me.
Yes. Sir, actually, I have one question. You said about the texture in the tool.
Yeah.
So that are the plain pattern. So what will happen if we select nature-inspired textures?
See, while making the textures over the tool, of course, we are interested to make the texture over the rack face. So if you are choosing the nature inspired, so we also have to think about the what to call the BUE, the build-up edges. So those structures should not act as a build-up edges. Otherwise, they will be the barrier towards the flow of the chip. So these textures are basically fabricated inside the pocket. First, we created the pocket, and within that, the textures are fabricated. So if you are fabricating the nature inspired, so anything that you are fabricating should be axis symmetric or symmetric about its axis, because we do not know from where the coolants are coming. Coolants can come from anywhere. So we do not know the flow direction of the coolant. So we are not very much directional about the textures. So that's why we kept the circular pillars. Any nature inspired, for example, aerofoil, right? That can work here, but only when if you have the directional penetration of the fluid.
Okay. Okay. Thank you, sir.
Okay.
Thank you, sir. Your presentation has. Thank you, sir. Your presentation has truly magnified the micro machining processes for us.
So, thank you
And
very much.
it will indeed inspire the participants for further exploration in the field of advanced machining processes. Thank you once again, sir.
Thanks.
It's now time to felicitate our dignitaries with mementos as a token of appreciation. I request Dr. Anil Kumar Tiwari, sir, to please come on the stage. I also request the Vice Chairman of the conference, Dr. Mahesh Bhivapurkar, sir, to present the memento to Tiwari, sir. Thank you, sir. With this, we conclude the first plenary session of the conference. I now request the participants and student coordinators to join us for the technical sessions at the designated venues at 2:45 p.m. after the networking lunch. The lunch will be at the cafeteria towards the right to your exit. Thank you all.